Well, welcome all to the June edition of Space Data Hackers. And couldn't be more excited about this particular talk because I have always been an astronomy nerd from way back. Love big telescopes, and we're going to be talking about those tonight. For introduction, for those who don't know who we are or what we do. Next slide. I'm Mike Doyle. I'm president and co-founder of Space Northwest. We are a nonprofit dedicated to maximizing the impact of the Pacific Northwest on humanity's future in space. With me is Eric Veal, who is co-organizer for Space Data Hackers, CEO and founder of AppsJack LLC. And a little bit about Space Data Hackers. If you're new, if this is the first time you've joined us, we're a community of people who love space and data and want to do great things with it. And we welcome all skill levels, all backgrounds. If you've got an interest, if you've got expertise, you can dig into space and data here to solve problems for our communities and navigate towards humanity's future in space. Okay, so tonight we got a little bit of the welcome out of the way. We're going to have our presentation and afterwards some Q&A, and then just open forum for folks to connect and talk about what's on your mind, what projects are you working on, what things would you like to do with space and data. And I will move us along to, I have to take a few minutes here to talk about Seattle Space Week, which was the week from Saturday, June 18th through Thursday, Saturday, June 8th through Thursday, the 13th. It was really a kind of festival of all things space. There were 6 or 7 different events that happened for all kinds of backgrounds and interests. There was a new exhibit that opened at the Museum of Flight, Human Home Beyond Earth. Definitely, if you're in the Seattle area, you should get to that museum and check it out. It's really cool. There was a uniquely entrepreneurial talk on Monday that brought together founders from the startup community in Seattle and beyond. We had a space and AI talk. We had the State of the Space Industrial Base workshop. There was the space ball outing at T-Mobile Park at the Mariners White Sox game. It was a lot of fun. It was the first time that Space Northwest has helped to coordinate and bring something like that together, and we're looking forward to doing it next year. Big shout out to Vanessa, who's on the call tonight, who did a lot of the marketing on that. Without further ado, our speaker tonight, Chris Suberlak, postdoctoral researcher at University of Washington, born in Poland, got his master's in physics at the University of Oxford and a PhD in astronomy and astrophysics from University of Washington. Currently pursuing research in astrophysics and specializing in analyzing time series data to classify and characterize quasars and variable stars. Really cool stuff. And as well as working on the optics, the active optics system for the Vera Rubin Observatory. Pretty awesome kind of background and a really exciting mission that you're working on, Chris. And I will stop sharing my screen now and hand it over to you.
Okay, thank you, Mike. Oh, disabled participant screen sharing. So
you got it.
Okay,
you're okay now.
That's right now. Okay.
Yeah.
I think you should be able to see the presentation now.
Yes.
Yeah. Okay, great. So welcome. I will start from brief introduction. You have already introduced me. Thank you for that. But just to give a little bit of background about myself, I was born in Poland, in geographical middle of Europe. I moved for my undergraduate studies to England, specifically University of Oxford. That's where I spent my 4 years doing undergraduate, including masters in physics and astronomy. From there, this is St. Hugh's College, that's where I was in Oxford. From there, I moved west, just keep going west. The arrow here is almost exactly following the same path as the airplane takes, flying the shortest distance.
Great.
Yeah, at least in this projection. And so I came here to do my PhD at UW in 2013. So I couldn't not show the physics building here with the very modern statue. And in the meantime, during my PhD, I got married to a wonderful artist. Then I obtained a PhD. And in the meantime, we had 4 children. 3 are on this graduation photo from 22. And we live a little bit south of Seattle, but I still commute pretty frequently to the office at UW. That's where I work. Right now, I'm a postdoc working for the Vera Rubin Observatory for the commissioning team in the active optics system group. So those are a few snapshots of my visit just last year. And in a couple of weeks, it's going to be another visit to the actual observatory. So in this talk, I will touch upon a lot of elements that Mike has already mentioned that I was involved in. So a little bit of science, mostly from the aspect of science being the driver and motivation for the construction of the telescope. Then the system design. So what are the main aspects of the telescope structure, of the key numbers that define the performance of the observatory? And finally, active optics system, which is the subsystem at the core of the telescope that I'm mostly involved in. So first, what science motivated the construction of this telescope? There are 4 major areas that people always talk about when they mention this telescope. And they range from largest scale all the way to our very solar neighborhood. So the expansion and history of the universe and growth of structure, we want to understand what is the spatial distribution of galaxies, key questions, big questions really. What's dark matter, what's dark energy? There is lots of ideas about that, but there is not a definitive data set that could give us a very good answer. Gravitational lensing, supernovae, understanding the variable sky, so things that weren't there and now there are, or maybe that were there and suddenly disappeared. So how does the sky change over the function of time? That involves things that we might expect or things that we might not expect. The Milky Way structure, so the dynamical content of the arms, the bar, the remnants of its previous interaction with other surrounding galaxies, all the so-called galactic archaeology that we can infer based on stellar populations, properties of stars in our Milky Way, etc. And the solar system structure. So not only understanding the location of various elements, we already know about planets, we know about thousands of asteroids, but improving these population studies. So what is the composition of those asteroids? What is the composition of trans-Neptunian objects? How many objects similar to Pluto are there? Finally, near-Earth objects and objects that might be hazardous to Earth. Are we going to be able to detect them soon enough to be able to do something about that? All of those different scientific questions were main drivers towards construction of a new telescope. And that now I'm going to slightly touch upon each of them just to give you an illustration of what is meant. In time domain, we think of a rapidly changing sky. Sky looks one way today, and tomorrow you might think that it looks exactly the same because the constellations are there, main stars are still there, but there is actually lots of things that change. So imagine that you take with your telescope image number 1, image number 2. The difference between the two might be nothing, just noise. So that means that nothing really changed. But if you take image 1, image 2, and suddenly something changed, it will pop up as a difference in that image. And you want to know, what is that thing? Is it a supernova? Is it something that I should perhaps follow up because it's one in a century event that you immediately want to follow up with Hubble, James Webb, and all the other telescopes? Or is it something benign like a satellite trail that you would rather ignore? Or maybe it is some asteroid that is heading straight towards the Earth. Maybe it's an interplanetary interloper, one of those asteroids that come from outside of our solar system. So all those things could appear as this simple dot on the image difference. There may be lots of properties of that as it changes over time, but that's how it all starts. That's the transient sky, that ever-changing night sky. Time domain also involves all sorts of astrophysical phenomena, such as supernovae. There is plenty of stars that, like red giants, that come to the end of their life. They produce a core collapse supernova. There is plenty of systems that are accreting actively onto a white dwarf. When you reach a critical mass, you never know exactly when it's going to happen. So you cannot say, oh, I have to stare at this particular star, because you don't exactly know when it's going to happen. The model can tell you plus minus 5,000 years. So you really have to just look at all stars in order to be able to catch them. And many of those still today are brought forth by amateur astronomers. But a dedicated survey to look for transient objects that appear suddenly and need to be followed up is something that is really needed. Stellar mergers is another origin of a transient phenomenon. For instance, you have two neutron stars that are orbiting each other, and at some point they merge, they produce a kilonova, an event that is even brighter by an order of magnitude than a supernova. And again, you didn't know where it was going to appear on the sky. So you almost have to be looking at the entire sky every single night to catch those phenomena. Similarly, tidal disruption events, those are moments when a star is unfortunate enough to pass very close to a supermassive black hole and gets disrupted. Suddenly you have a brightening event, or a nova, where you have accretion of mass onto a dwarf, and again you have an explosion, but just on the surface, not the entire star, so it's slightly less luminous than supernova. But a lot of these things are either one-off or things that you might be able to track, or things that have aperiodic behavior. So a lot of those things are simply unexpected. A lot of those things are expected, in a sense that we know that certain stars change their variability. There are catalogs of those stars and their patterns of variability, but all those catalogs are limited by how deep any telescope can look. There is a ZTF survey and other sky surveys, but they only go far enough because of the limitation of the mirror size. Also, many telescopes only run for a couple of years, and they do not provide continuous monitoring. This light curve, which is a plot of image brightness over time, illustrates a coverage of a particular object called a quasar. So it's an actively accreting supermassive black hole somewhere across the observable universe, where the amount of fuel falling onto a supermassive black hole changes as a function of time. It can be described by a stochastic process called damped random walk, and it's best to observe those for an extended period of time. Given that the characteristic variability is on the order of few hundred of days, there are papers that show that you need to observe it at least 10 times longer than that. So 3,000 days. That already goes into years. And here you see that the SDSS data, that's the red, only spans about a decade. PS1, another sky survey, only spans a few years. And that's it. And each of those has a much smaller telescope than what is planned for Rubin Observatory. So when you jump forward to the operation of Rubin Observatory, the accuracy for objects that are very faint, like quasars, is exquisite. All those points include error bars, but the actual error bar is smaller than the dot itself. So LSST is going to provide light curves of tremendous value for thousands of quasars like that will allow us to much better characterize properties of quasars that are reflected in their light curve. Another area of focus, apart from time domain, is the makeup of the universe. So location of galaxies. Each dot on this image is already an observed galaxy from an SDSS, Sloan Digital Sky Survey. And you can see that their distribution as a function of distance from us, so as a function of, we are in the center of that circle, and the further to the perimeter, to the outer part of the circle, the further away this object is from us. So you're looking deeper and deeper with increasing radii into the universe. That's reflected by the redshift measure. And you can see that the distribution of galaxies is not uniform. It's actually highly inhomogeneous. And details of that distribution contain a lot of cosmological informations, because you can distinguish cosmological models by the two-point correlation functions, for instance, that describes the spatial distribution of galaxies. And again, that was what we already know. With LSST, we're going to see about 10 times larger of a distance. So this gray circle is what we will see once the telescope becomes operational. We'll be able to map galaxies over half the sky, including over 20 billion galaxies. So the sheer improvement in the statistical measure of the number of objects involved was one of the motivations for the telescope. Even all variability put aside, just the number of galaxies. That was one of the main science drivers. That's why the telescope is designed as a survey telescope, because of all these constraints for discovering the unexpected, looking for the unknown, being able to scan the entire sky in a very uniform fashion. The majority of the time of the telescope will be spent in this wide, fast, deep survey. That's a survey that will provide about 800 visits over 10 years. So each location in the sky will be visited about 800 times. That's where I got points for that light curve on the previous slide. I had about 800 points scattered over the period of 10 years. And each of those billions of galaxies that will be measured will actually have not just one, but 800 measurement points. So if there is any variable object, a light curve will have 800 measurement points on average. There will be those parts that have slightly less observations, and that's simply reflecting the galaxy itself. We're avoiding the dust, because that doesn't allow us to see really beyond the dust. You just see the dust, so you can study the dust and the properties of how the dust is distributed throughout the Milky Way, but then you cannot really see beyond it very much because of the dust absorption. So that's why there is this darker part here that's called exclusion zone. We're trying to avoid observations in those regions. But apart from that, everywhere else, we're looking at roughly 800 observations over a period of 10 years. So that will result in about 2 million of 3.2 gigapixel images, which is about 64 petabytes of raw data. So that means that in one night, this telescope is going to produce the same amount of data that the SDSS survey produced over its entire lifetime, which was 10 years. That's how much more information there will be in this observatory. The point of the survey is not just to take the image, but also to process them and produce user-friendly catalogs, including all sorts of model parameters that are fitted to all the observed sources, which would mean about, yeah?
Is the horizon there? It's not between the unobservable area and your observable area. Why is the
Yes.
horizon shaped like that? Is that from local orography, the horizon around the observatory?
Yeah, there are little parts here that have to do with where you're looking, and I think if you put it in another projection, you would see that it actually corresponds more to a flat line of the observatory.
Okay, thank you.
So let's show some pretty images, what we're going to be looking at. This is actually an old image from SDSS survey, 3.5 by 3.5 arc minutes. That's one snapshot that this new telescope in construction is going to take. 3 arc minutes, which is the width of that, is about 1/10 of the full moon's diameter. So we would be able to fit 10 full moons across here. So that's actually a huge area of the night sky. And with LSST, voila. It's quite a bit deeper. You can immediately see many more objects. All the galaxies are sharper. Of course, they show much more low brightness features. You might have some distant red dots that could be galaxies across the observable universe that are so far that they are redshifted. So just flicking between the two shows you, how much better this new data will be compared to the previous state of the art, which was SDSS survey. This survey will comprise of 2 times 15-second exposures back to back. The nightly data size, as I mentioned, will be 20 terabytes. So that's roughly the size of the previous survey altogether. The entire SDSS over 10 years produced that much data. The final database size will be measured in tens of petabytes. And real-time alert latency is what we want as a target timescale over which the information about some potentially very interesting object that should be followed up by astronomers across the world would be publicly available. So 60 seconds from taking the image, it's fully reduced, cross-matched against all templates of existing images. And yeah, and in that time, from about 10 million alerts that would be produced, so 10 million of anything that shows up on the sky, we filter out all the bogus stuff. So all the, image noise, cosmic rays, satellites, all that stuff is gone. Wind it down to hundreds of thousands, fit all sorts of models. So we fit a model of, okay, what should the color distribution be of a supernova? What is our prior Bayesian information about stars in that location? Was there perhaps a red dwarf? Was there a white dwarf? Was there a supergiant in that location? So all sorts of information that can help us quickly figure out what is that thing that just appeared on that image. And all that has to be done within 60 seconds because that's one of the requirements. To be able to very quickly follow up. Yeah.
Is that happening, that pipeline local at the observatory?
It's distributed actually. So this is handled by alert brokers. And there is several of those. Alerci, Antares, that's a whole other talk. But those brokers are actually taking in the raw data and which goes, one of that will be on site. That's correct. Just in case all fiber optic cables fail and communications fail, there will be processing on site. But that's limited. So immediately the data reaches Stanford. That's at SLAC. That's one of the US-based processing centers. Another one will be IN2P3 in France. Some of those will be in the cloud based at various universities. All of those will be able to take that raw data and produce their own alerts and interpret in a way their own results. Just so
Amazing.
that you have, a cross-validation, so that it's not just a one source of alerts. There is one official source of alerts, but there will be several unofficial alert brokers. That will then, quickly, they all have a pretty nice user interface where you have a website UI, you can see where is that alert, what sort of information is available, what's recommended, what's the likelihood that this object is, for instance, a supernova or a nova or a TDE or anything else, maybe, a gamma ray burst, stuff like that. That's a whole other talk. Here I'm just mentioning it in passing, really. And all that data, both the alerts as well as the each night summaries and the data releases will be available through Rubin Science platforms. Rubin Science platform will comprise of a portal, which would be familiar to people who used like the IPAC, the infrared processing data center at Stanford, or Mikulski archive from NASA, or any other astronomical data archive, which usually has a user interface that allows you to click which columns you want to kind of make a cone query, rectangle query, or perhaps cross-match against a list of your favorite objects, see images, see catalogs, value-added products. But a new thing that currently I think is only available with Noir Lab is notebooks, so that a user can register and be allocated a certain amount of computational power in the cloud, so that he doesn't have to download 20 terabytes of raw data. He can interact with the data in the cloud using this resource and, for instance, download the result of the analysis on his laptop for further analysis, or maybe do his entire scientific analysis on the cloud, because that would be possible as well. And other APIs that will allow you to query with, for instance, TAP protocol or any other way of quickly querying for the data, just like currently is available for SDSS, ZTF. So because of the funding structure, all of that is meant to be publicly available. This implies that there is quite a complicated flow between observatory operations and data production that I already mentioned, cross-matched with system performance that continuously gives us information about the operation of the telescope and what it does, and if there is absolutely any issue with it. With public outreach, there is already a whole EPO section of the telescope operations, which produces stuff that helps to engage public. So instead of making it kind of behind glass ceiling, only intelligible to scientists, this education and public outreach branch will help average person actually see the real data and even understand what sort of science can be done with this data, what sort of information is there. You don't have to just wait for the press release to be excited about the data. Maybe you can play with the data yourself, or do some science citizen discovery that has been done in the past. So a lot of these things can be utilized in this observatory. So given all this science motivation of, lots of data products and exciting stuff that we expect that should be possible, what was the actual design that would fulfill all these requirements and bring us all the promised data products? First, I need to mention that it's ground-based. Space is great, and it's ideal because there is no atmosphere between you and the star. But it is pretty complex to get there. There is a cost. Payload is pretty expensive. There is a lot of risks associated with launch, like with JWST. Everybody was wondering, is this, project gonna get buried just because the rocket has a malfunction during launch? It's all eggs in one basket with this kind of huge observatories. Difficult to service. I mean, you can just think of Hubble and all these initial problems with optics and how it took some astronauts to actually go there and do the servicing when they had to realign the mirrors. With ground-based, it's second best, since you have the atmosphere between you and the star, but it is easier to repair. You can certainly put larger aperture on the surface of the Earth. And ideally, when you're thinking of a ground-based location, you want to have it as high as possible so that you have as little of atmosphere to contend with. You want to have a dry climate so that you can simply spend as many nights as possible per year in photometric condition. And people always think of stable access. So how do we actually get there? Is it hopefully in a stable region as well, so that, the telescope is not going to get impacted by an earthquake or some civil unrest or just about anything that would hinder science? Of all those considerations, several sites initially were thought to be fulfilling those requirements. One in Mexico, one in the Canary Islands in La Palma, two in Chile. But of those 4 sites that passed all these criteria, the final one was Cerro Pachón in Chile. It's about an hour flight from north, from Santiago. The nearest big town is La Serena. And from there, you have to take about 50 kilometers of a paved highway. And then there is a turnoff on a private Aura land. Aura is an association of universities for research in astronomy. They maintain and operate this telescope by a mandate from NSF and DOE. And after over an hour of being driven in this dirt road, you finally arrive at the location of LSST at an altitude of about 2,600 meters. So what's interesting about this location, and that you can see from the map, is that between you and the Pacific Ocean, you've passed quite a bit of elevation and orography. And that means that thanks to thermal inversion, that even if it's cloudy down there and foggy and misty, as it often is in La Serena, as soon as you arrive at the observatory, all of these things are beneath. And you can simply see the sea of clouds underneath the observatory. That's what it looks like from a nearby location. 2 telescopes are already there, Gemini and SOAR. And the third one is on the right-hand side. That's Rubin Observatory. That's the small dot on the right-hand side. You can see them as you fly in your telescope. If you fly even as a, for business to Santiago from, for instance, I flew from LA to Santiago, you will pass over those telescopes. It's a large observatory. It's not just a building for the telescope. It actually has a vertical platform to be able to get the entire M1 and in the entire mirror from the coating chamber up the lift to the telescope and back down, because a mirror has to be periodically recoated to keep the image quality at top notch. And there is lots of other engineering. Yes? Don't ask me about time. I think it's about every couple of years. I'm sorry, say again.
I'm so impressed. It's not just the telescope. That's a rather sophisticated manufacturing repair operation at that altitude in a clean room condition.
It really is, especially considering that you have to take these 50 kilometers of paved highway and then, further 40 kilometers or so of a dirt road. So it takes 2.5 hours by bus from La Serena, from the headquarters. There is a whole compound with various operational buildings. that was already there, built for other telescopes that were in the area. That was one of the reasons why they chose that location, because the road was already there, built to access to other telescopes. So all they had to do was clean up another mountaintop to build that observatory. But doing that took a while. And here is a short illustration. 2011, breaking of the ground, and then time lapse of what it took for over a decade, really, to construct the telescope. Year after year, building the enclosure, the on-site engineering, not even fully housed by 2017. One of the core elements you might have noticed is this very heavy concrete block that isolates the telescope from the surrounding dome, so that opening and closing the dome doesn't actually affect the telescope. It's vibrationally separated. That's this big circle inside. And you can also see this small telescope on the right-hand side. That's the auxiliary telescope. 2018, it's almost completely finished, the dome. And I think the final frames here go to 2022, when the dome is fully covered. That's those two things that stick out. Those are the shutters. That's where it opens. Yeah.
So
Here
are
you
the
can see it
louvers
opened up.
along?
Yeah.
Are the louvers along the side? Do those assist in the climate control, or those open programmatically to? Wow.
Yes, precisely. Yeah. That's to keep the temperature differential as low as possible, because you want to minimize the amount of temperature for others on the call. You want to minimize the temperature differential. Even an amateur observer many times will have like a little fan to make sure that your small telescope doesn't have a temperature differential from the outside, so that those little currents that would form would actually be blurring your image. So that's what the louvers would be for. Okay, 22, that's the end. And ever since, it looks pretty much the same on the outside. The main improvements here are on the inside, where they installed the TMA, the telescope mount assembly, and all the elements. Let me shift to the next one. That's May 24, so just a month ago. So you can see it looks exactly the same. Louvers are there. The entire telescope housing is there. The auxiliary telescope, that's the tiny dome, houses 1.2 meter telescope that has been in continuous operation and is used as a pathfinder for the science pipelines, but also it will be used as one of the follow-up telescopes, because it has a tiny spectrograph. So it will be one of the instruments that could be used to follow up a target while the main telescope is taking its data. So trying to move towards the optical design, this telescope was optimized for transients. So that means you want to have a large field of view, large light collecting area, and at the same time, you want it to be able to move as fast as possible from one location to another, to be able to scan the night sky and take images one after another, 30 seconds, 30 seconds, 30 seconds, minimize the dead time of slewing from one position to another. You also want to have multiple filters and as many field revisits as possible, because that would allow you to discover potentially something that wasn't there before. Multiple filters, because many things for many objects, chromatic information acts kind of like a cheap spectrum. Instead of taking a full spectral energy distribution, you might have multi-wavelength information. I think some satellite people call it hyperspectral. So you have information in multiple filters for exactly the same image. And that helps you to identify, just like looking on the Earth, you can distinguish grass from rock based on this kind of different filter information. Here you can distinguish a supernova from a tidal disruption event because they will have different colors. So given that we're trying to optimize it for transients, the optical design is a very short telescope. It's a 3-mirror Paul Baker's system that enables a large field of view. It's 8.4 meter in diameter for the main mirror, then 3.4 meter secondary, 5 meter tertiary, and both the primary and tertiary are actually one solid block of glass. They just have 2 different curvatures.
Wow.
And 3.5 degrees field of view. As I said, it's 10 times the size of a full moon. So it's really vast. The camera itself weighs 3 tons. And this M1, M3 monolith weighs 16 tons. So altogether, for me, it's one of the miracles of engineering. How can you move this thing so easily? Because allegedly, it is so well balanced that you could move it with one hand, the entire structure. And I saw how it moves. It doesn't use ball bearings. It uses superconducting magnets to minimize friction.
Amazing.
Yeah, it's lots of cool engineering solutions that go into it. Now, a short animation of how the mirrors work. They're pretty unique because you have 2 different curvatures, and this 8.4 meter mirror first bounces off the outer surface, then you bounce off the secondary, then the tertiary feeds into the camera. The lenses are there to make sure that it's as flat as possible, so that because it's hard to bend a CCD is usually flat. So that allows you to take those images. Next, the field of view. Compare that to other telescopes because we want it to be as good for transient discovery as possible. So we want to have as large of a field of view. Let me give a sense of perspective of how this fares compared to other telescopes. Gemini is another 8-meter class telescope, but it doesn't have that design of 3 mirrors that allows it to be very short. Gemini is more traditional in that aspect. And so the field of view is only 0.2 degrees. So it's tiny compared to the 3.5 degrees of Rubin Observatory. In fact, in comparison to other observatories, the size of the mirror is also not superb. There are observatories that have 20 meter, 30 meter, 40 meter class mirror size. But what is unique about Rubin Observatory is that it will have by far the largest product of the mirror area and the field of view. And that's shown here on this plot. You have lots of different surveys. On the y-axis is the field of view, so how much of an area of the night sky you can see at once. And on the x-axis is the light correcting area in square meters, so the size of the mirror. And that can roughly translate to the limiting magnitude. How deep can I look with my telescope? So there are telescopes that can look pretty deep, like the MegaCam, but they're not looking at a very large field of view. So when you take the product of them, the circle will be small. And those diagonal lines correspond to constant throughput or constant product of light correcting area times the field of view. So you see that LSST or Rubin will really have the largest throughput of all telescopes considered, larger than Zwicky Transient Factory, TESS, Kepler, and many other observatories, several times greater than SDSS that I was showing before. Similarly, much greater than Pan-STARRS. Having spoken about the mirrors, now it's time for the camera. The camera will have 3.2 gigapixels. So that's one of the best of, because it is the largest astronomical camera in the world. It's 2 feet across, and it has 189 individual CCDs. Each of those CCDs, by the way, sits on its own individual raft, so that in case of some catastrophic failure, instead of having to monkey with the entire detector, you can pull out one CCD and replace it. This camera has so much resolution that it would take about 1500 HD TVs to display a single image, this 3.5 by 3.5 degrees. So that's what it would look like. I always find this slide hilarious, because it would be quite a large display. And it would take 11 months to view all images that were taken by the survey. If you were going to display one per HDTV frame with 1 per HDTV screen with 30 frames per second. So it would be a pretty long movie of the night sky. This camera looks in the optical and stretching slightly to near infrared, especially in the Y band. The U filter goes pretty close to the blue end of the spectrum, going all the way to 1100, which is the Z, which is the Y band, ZY. The funny shape of that is because filters themselves have throughput that has a flat top, and as they're sharp, so they go quickly up, stay flat on the top, they quickly go down, so that the filters have a well-defined edge. An ideal filter would be really a top hat, but here they are multiplied by the quantum efficiency of CCD, which drops dramatically in both in the UV and in the infrared. So that's the property of the sensitivity of the material. And on top of that, you have the transmissivity of the atmosphere, which has quite a few of those bands where less light gets through. And that's why, for instance, in the I band, there is this big dip. Filters themselves have to match the size of the CCD. So if the CCD is 2 feet across, the filters have to be at least 2 feet across as well. So if you ask me, that's a pretty big astronomical filter. All of those filters surround the camera so that they can slide in front of the detector. You take 2 back-to-back 15-second exposures, move the filter out, move in another one, perhaps slew the telescope, and keep doing that with minimum engineering interference. The camera already arrived. This complicated structure had to be taken on this dirt road very slowly, all the way up to the top, disassembled, mounted onto the telescope. The mirror itself has been coated just last month. That's a short, I might speed it up just to show you that the mirror is there, the camera is there. So everything is really coming together as we speak. That's the inside.
Who built
camera.
the camera?
Camera is from Stanford. Mirror was cast at University of Arizona under their stadium. There is a huge Harris mirror lab. They also cast several other mirrors, so they have lots of experience with casting mirrors. And here they show how they first removed the protective layer, then they add several protective layers, they deposit silver to actually make it reflective, to make it a mirror. And after it's all done, you get from a piece of glass a piece of a mirror. And that was a great thing to see, because I've seen it as just a piece of glass, and now it really looks like an astronomical mirror. And that's why we need this chamber, because this process will have to be repeated several times during the duration of the survey. It's, for instance, because of dust and anything that deposits on the surface of the mirror. Finally, having talked about a little bit of science drivers and the system design of camera and all the mirrors, I will describe a little bit of active optics system, and that has been my involvement in the construction commissioning. The main components, well, what is active optics? So active optics is a system that is designed to optimize the image quality. How do you do that? You control the actual curvature of M1, M3, so this main 8-ton mirror. M2 also has its hexapods. Even the camera has hexapods and the rotator. So you're controlling the relative position in over 50 degrees of freedom for all of those components to improve the image quality. This little schematic shows you 156 actuators for M1 and M3 that support the telescope. M2, the secondary mirror, also has its own actuators.
How
And
thick or thin is the mirror material itself that it can be its shape altered by these actuators?
So it has those empty pockets, which is why it can slightly bend, very slightly. No, we are not talking even of millimeters, but it can bend.
Even if it's nanometers, it's amazing.
Yeah, but it is a rigid body. So it has those empty pockets so that it would be as light as possible. So it's not like a piece of a solid. It actually has those drilled pockets inside. But yeah, it is possible to bend it ever so slightly. The active optics system has two components. One of them is what is called closed loop, and that's lookup table. It's based on the finite element analysis, so the analysis that was done even before the mirror was cast, then based on the optical design of the mirror, then after the mirror was cast, on the laboratory measurements of its properties, or the tonsile strength, all sorts of properties about how does it behave as you move it to different angles. That's what we mean when we talk to gravity. When we move the mirror to different altitude and azimuth, you're actually, changing the forces of gravity that are acting on the mirror. Finally, temperature gradients. If there is any sort of temperature difference across the mirror, or perhaps in the observatory, this would cause the mirror to slightly expand, slightly contract. Of course, they use the mirror. Of course, they use for optics a material that has smallest possible thermal expansion coefficient, but it still does it. So you have to correct for that, and all of that can be pretty much taken care of with this closed loop, with the lookup table. That's a static element that has been refined, and it can quickly tell us what should be the forces provided by the actuators given this altitude or this zenith angle and this temperature gradient. Those are the two main elements. But the other component is the real-time open loop that analyzes images that were taken on a 30-second time scale, so those two back-to-back images, and that affects information that we couldn't possibly obtain before, such as the dome seeing at the moment of taking the image, or the atmospheric turbulence at the moment of taking the image. We can measure the seeing, but seeing is already a metric that summarizes a lot of individual components of atmospheric turbulence. So that helps us to get a in real-time information, and that's what I will really focus on in the next few slides. So this real-time analysis is performed using wavefront sensors. We have the entire focal plane, and most of the sensors, the blue, are the science sensors, 189 science sensors. Apart from them, we have guide sensors and wavefront sensors. Guide sensors are sensors that would take images of stars and would be cross-matched mostly for positioning. But wavefront sensors are designed to be in and out of focus. They are in 4 corners of the field of view, those 4 corners. And each of those detectors is by design slightly out of focus. This is actually from an old paper, so it's not 1 millimeter, it's 1.5 millimeters. 1.5 millimeters in focus and 1.5 millimeters out of focus. Because of the annular design of the mirror, so you have one mirror that's actually an annulus, an in focus point source becomes a donut. So that's why in any sort of defocal image that we take with this telescope, instead of just a blur, you actually see donuts. That's what the blurred image looks like. And we have tested the pipeline in a variety of stellar densities. Those stellar densities correspond to different locations in the galactic plane. So high, medium, low latitude. And thankfully, when you take an image out of focus, a lot of background also becomes out of focus. So overall, the surface brightness goes down. So even if there was a lot of overlap, you end up with slightly less overlap when in terms of donuts overlapping each other. We still have to deal with that, but that shows you that in-focus images become out of focus donuts at varying degrees of densities. Sometimes you have very nice isolated donuts, but sometimes you have fields with very blended donuts, one on top of each other. And we have to be able to obtain information from all sorts of environments like that. So those defocal images are analyzed in order to describe the wavefront. The wavefront is most of the time characterized as a departure from the ideal reference sphere. The real aberrated wavefront will have some imperfections due to the shape of the telescope that you didn't consider. Here, this is compared to the reference sphere. In our case, it would be a reference fiducial model of the telescope. That we have this ideal model of the telescope, and yet we are measuring an aberrated wavefront. And it's aberrated by anything that we didn't include in our model. And how do we describe this aberration? Most of the time in optics, people use an orthogonal set of polynomials called Zernike polynomials, after Fritz Zernike, who first came up with that. Just like you might have heard of Legendre or Bessel or any other set of orthogonal set of polynomials. Those are useful for optics because they are orthogonal on an annulus. And each element of this expansion corresponds to a slightly different optical aberration. So not term 4 looks like a defocus. Term 5 and 6 looks like primary astigmatism. 7 and 8 like primary coma. 9, 10 like trefoil. And each subsequent element introduces more and more modes in which you can have an aberration, an optical aberration. So the closed loop, this real-time feedback, works by taking in the surface model and the telescope model and comparing it with the simulated image, finding the difference. And the heart of the algorithm is the transport of intensity equation. That's the only equation I have here, so don't worry about it. It's the change of intensity as a function of distance. So as the rays of light go through the optical axis, we point Z towards the sky. If you put the mirror flat, then Z goes straight up. So this is the change of intensity as a function of distance. And the right-hand side is a divergence of a product of total intensity and the gradient of the wavefront. Wavefront is what we're trying to infer. And intensity would be the total intensity of the image. So from these defocal images, you can think of it that we are approximating the left-hand side of this equation by the difference between the two images, because that would be the gradient over the distance of 3 millimeters. plus 1.5 minus 1.5. And the total intensity would be the sum divided by 2, the mean of the two images. So you have the gradient, you have the total intensity, invert that and get the wavefront. So that's what is done in a variety of ways by the algorithms that are at the heart of the active optics system. We solve for the wavefront in Zernike basis. And that way, having the expansion of wavefront in Zernike basis, we're actually able to correct forces for the hexapods that slightly change the position of optical elements and improve the shape of the mirror. And we actually validated the entire algorithm by simulating a telescope that is slightly imperfect. So we throw into the simulation the fiducial model, and on top of that, we add some perturbations, either to both mirrors or to both or to the camera, just to test how it behaves. Small perturbations, large perturbations, perhaps one Zernike mode at the time, perhaps a random distribution of all across all Zernike modes, plus minus 100 nanometers, for instance, in Z7. And we look at how does the algorithm, how well does it retrieve the input values. And given the input values, it produces the optical feedback corrections that then simulate the next image. And the next image now has a corrected shape of the telescope. And we redo that over and over multiple iterations. And what we see is the convergence, because if we are finding that the initial corrections were good enough, then the image quality metrics should dramatically improve after the first iteration. And then in the subsequent iterations of that simulation, they should only improve very slightly until you reach the threshold that you basically cannot go any further because of noise that is also simulated. And that's what we see. We have already validated that over the past years of designing the system. The image processing is pretty interesting itself, because that's what you deal with both in real life and in simulation. The telescope is not yet fully operational, so the camera is on site, but it's just being integrated. This is the simulated commissioning camera image. Commissioning camera is one of the rafts of the telescope, so 9 CCDs. And this is one of those CCDs, which has 16 amplifiers. That's why you have 16 distinct rectangles on the left-hand side. That's the raw image. Each amplifier has different gain, different noise properties. So you have to stitch it all together, correct for all that you know about based on the properties of every single amplifier, and arrive at the post-ISR image. ISR is instrument signature removal. So we call this raw, what arrives from the telescope, and then you conduct the instrument signature removal using your calibration frames, the flats, the darks, and anything else that is available. And given this ISR image, we run the AOS. We, for instance, cross-match the detected donuts with Gaia star catalog. This is a bright star catalog, but they have very good location because they have very good astrometry. And based on that, we cut out those donut images and run our pipeline to figure out what is the wavefront based on each individual donut pair. Then we have a way of combining this information so that you have some sort of average Zernike wavefront per wavefront corner. We average all those corners. There is also separate ways, because this averaging can be done in various ways. You can reject the outliers, you can do sigma clipping. Yeah.
So in operational mode,
Mm-hmm.
is it using historical astronometry for ongoing calibration, or was that only used in designing and developing it?
So both. So Gaia has supremely good astrometry. It's because astrometry is the position of the star. Photometry is the brightness. So it has very good information about the XY location, or really array deck on the sky of the source. And given that it has such good location, we can very quickly cross-match the catalog of sources on the on the raw image to the catalog of sources from Gaia, because we know roughly where the telescope is pointing on the sky, but then you do this cross match to arrive at the precise world coordinate system solution, the WCS. So that you have a very good WCS attached to the image, and then you can pull in sources from Gaia catalog, but you can also do direct detection, cross match it against other catalogs. But really, as the telescope goes, you're right. For those donuts, we are looking at very bright sources. So the limit here is from 8th to 15th magnitude for donuts. So we're looking at very bright sources. The single visit 5 sigma depth for R-band will be 24.5. So there will be plenty of in-focus stars in the image that when you take it out of focus, you will not be able to see it at all. And a 15th magnitude donut is already pretty faint.
Yeah.
So to be honest, you don't really need a perfect star catalog for that kind of job. For detection of transients, that's a separate question, because for an in-focus image, you really have, lots of sources that go all the way to 24.5 single visit. And then the visit from one night gets co-added to the visit from other nights that happens to be in exactly the same location, so that you keep building up the co-added template. And there will be a new template every data release, so that as the survey progresses, you will have better and better templates.
It gets better and better as the more you use it, in other words.
Exactly, because you will have more information about all sources, so that it will be quite easy to say, oh, this is a new source, not just because it's not in Gaia. Like Gaia has, goes only down to 18th. So already in the first few months of operations, we'll be going into uncharted territory. So
it's using actually two sources, the telescope itself and the external ones like Gaia.
Yes, exactly. For the in-focus
very
images.
Cool.
Yeah.
Yeah.
Because that will really streamline the alerts process. And, the catalogs, because the astrometric information about all sources will keep improving as you keep getting better measurements, because you have slight uncertainty about each pointing, even though you do this WCS cross match. So you have this array deck with certain error, plus minus, few, maybe milli-arc seconds. But then as you keep taking images of exactly the same source, you find that, oh, the location of that very distant galaxy obviously hasn't shifted because the galaxy hasn't moved anywhere. So the only thing that has moved is your centroid. So you will be able to take the average of all those measurements. So the position.
And it is one of the implications of this ongoing calibration is for hazardous asteroids and very faint things that might be moving very quickly across the image. Time goes on, you stand at higher and higher probability of capturing those sorts.
Exactly.
That's
because
very
if there is, that's a very obvious application.
That's pretty amazing. Very helpful in planetary defense. I see a question in the chat about how frequently does the telescope capture an image?
Every 30 seconds. So we take 2 15-second exposure back to back to minimize noise. And after those 30 seconds, you either stay in the same position and change filter, or you move to a slightly different field and take another exposure. And the AOS solution, so the image instrument signature removal, detection of donuts, figuring out what is the wavefront and what should be the corrections, that all has to be finished within those 30 seconds, so that it is ready for the next pointing. That's also an example of what we do in commissioning. That's a simulation of a focus sequence for a commissioning camera. Sorry, I assume there were no other questions, or were there? Should I be looking at the chat? Okay, good.
Okay.
Let me know. So this is another example of what we do in commissioning. We simulate a lot of focus sequences. So defocal images, pistoning the entire camera, the Raft 22, because Raft 22 is only the central raft of all those other rafts. It's only 9 CCDs out of 189. that we have on the commissioning camera. The commissioning camera is a smaller part of these 189 that doesn't actually have the corners, doesn't have the wavefront sensors. So the commissioning camera is just this one Raft 22, and we will still use it for testing of this active optics system by pistoning it plus minus 1.5 millimeters to make it work as if it were one of those corner sensors. And so that's what we do here, simulating those offset images, because you notice that those are squares. Like I said before, that we have those corner sensors, and each of those is actually 2 by 4K, right next to another 2 by 4K, one offset by plus 1.5, the other by 1.5, by minus 1.5. So they are 2 by 4K, and this is 4 by 4K. So that's because this is actually a commissioning test of a Raft 22, and you get all the out of focus donuts, in focus stars on and both sides of the focal plane. That was actually done yesterday, today, and tomorrow. We are feeding these kind of simulated images through the entire system, pretending that we are, running observations. So we are feeding blocks of commands to the telescope to, pretend that we are taking an image. The software thinks that it's a real image, so it analyzes it from a RAW to an ISR, analyzes the wavefront, applies corrections, goes to another place. And so this is called operations rehearsal. We are doing that tonight and tomorrow. This is the 4th one. Next month, we will have the actual commissioning camera. So all these simulations will be, hopefully a good preparation for what comes next. And I think the next is the last slide, just to show you another example of what the commissioning simulations are achieving. They simulate those out of focus corner sensors, show you what is the wavefront in Zernike basis, show you the postage stamp cutouts so that you can inspect the donuts and make sure that there is nothing wrong with the donuts. Active work continues on deblending, so there was plenty of overlapping donuts, and you don't really want to throw away this information. So what can you do? How can you mask one, perhaps, or maybe you can use both simultaneously using machine learning? All of those things are in active development. Another one is donut image quality check. So even though we have this Gaia catalog to figure out where the stars are and where the donuts are, what if something fails and we get a donut that is halfway on the cutout, and or maybe there is some problem with that amplifier that didn't get caught with the ISR, and we have some image that for some reason doesn't involve a donut. You don't want the pipeline to fail. So I was working on developing an entropy-based measure and signal-to-noise measure that would tell us, does this image look like a donut? Or does it actually have a lot of background sources or, halfway donuts that the pipeline didn't think it was a blend, stuff like that. And of course, operation rehearsals. I just mentioned that we're actually replaying those images as we speak. So I think I ran through it. That's all. I'll take more questions if you like.
I have a question on the names. Why Vera C. Rubin? Who is she?
She's
Simeoni, mispronouncing the name.
Yeah. There is
tell me a little bit about the namesakes.
Yeah, there is lots of acronyms here. So it started off as LSST, Large Synoptic Survey Telescope. So just a name that describes what it is. It is a large telescope that will take synoptic. Synopsomai means simultaneous, like synoptic gospels. So you have synoptic survey, looking at as many places simultaneously as possible. That was just the astronomer's name. And then came the funding. Funding was between NSF and DOE. I think I actually have one of the slides that explains the funding. There we go. So NSF funds Aura, which manages the project office. And DOE, for instance, was funding SLAC that built the camera. So it's kind of split between the two. So Congress had a say in what should be the name. And a couple of years ago, they passed a bill to name it in honor of Vera Rubin, who was an astronomer several decades ago. And she was one of those early astronomers that were thinking, oh, perhaps there is dark matter, even though there is almost no proof for it. She was just seeing the rotation curves of galaxies and saying, well, this galaxy seems to be rotating at the outer skirts slightly different than what you would expect if there were just stars that you can see. So she was one of those that were postulating perhaps there is some additional component of galaxies that we cannot see, and that's dark matter. That's actually aura. So it's hard to almost wrap your head around it when you visit the headquarters, because you see aura, you see NSF, you see DOE, you see all sorts of logos splashed around. Aura is an entity that manages not just LSST or Rubin, but it also manages several other observatories. And that's just a map that shows you, what do they manage? What's Aura involved in? Aura consists of quite a few universities. You don't even have to be a member of Aura to get Aura funding, but being a member institution helps to be involved. And main stakeholders in construction and operations of LSST are indeed members of Aura, such as Princeton, University of Washington, Stanford, and Simoni. Charles Simoni gave a big 20 million grant that was fundamental in being able to push for the construction of the telescope mount assembly and casting the mirror. So he gave this big injection of money when it was needed early on, and so he gets to commemorate his name in the main telescope, the Simoni telescope.
Very big donor to the Museum of Flight down in Tukwila as well.
Yeah, so
there's a gallery bearing his name.
Yeah, so that's why it's commemorated. It makes sense, and I think he was there at the opening, the first stone ceremony.
Awesome.
So taking into account the latitude that the observatory is at, and then the inclination of the Earth as it goes around the sun, and then the flight tilt of the solar system relative to the galactic plane, what is the coverage of the night sky sphere? And is there any push to fill in the blind spot, so to speak, an observatory to complement it somewhere else?
Yeah, so that would be a great thing. So the question is about, even in this simulation, you can see that it's in a slightly different projection, but there is this big void here. That's the northern part of the sky that this telescope cannot see. So it would be natural for another telescope like that to be deployed somewhere in the northern hemisphere. I have not heard of plans like that. For SDSS, there is actually a southern SDSS, that's SDSS 5, an almost identical telescope to SDSS. SDSS is a 2.5-meter telescope that is right now in New Mexico, not far from Alamogordo. It's managed by UW, for instance, and Princeton and several other entities. And they have conducted one of those early on sky surveys. That was one of the pioneering telescopes that would really just, instead of having a telescope and a time allocation committee and people who decide, okay, we're going to look here, here, and here because those proposals seem to be, most meritorious. It was all designed as a survey to just keep taking images of the sky all the time, as uniformly as possible. That was the first main survey that many people have, started working with, SDSS. And SDSS from the north has now a complement in the south. So who knows, perhaps in the future there would be a Rubin North to complement Rubin South. It's a very good idea.
Actually, it's kind of a problem as far as it almost inevitably ends up somewhere in the northern hemisphere, and most of the world's population is in the northern hemisphere, and the resulting light pollution. And if you think about the synoptic geography, there aren't that very many you know, locations, that situation down in Chile is like a convergence of many, you know, different factors for a observatory location.
Yeah,
And
I mean,
nothing.
it's a lot of factors. Like Hawaii is in the middle of the ocean, so it's a little bit hard to get to, but it's a US, you know, state. So that makes it easier when it comes to funding, communication, and everything, and politics. Chile is a different country, so already there had to be a lot of agreements and things that come into play. Because I mean, even if you're hiring an engineer, like, are you gonna hire an engineer that doesn't speak English? Well, probably Spanish, probably not. So you're likely to hire local engineers, and then there is all sorts of communication stuff, and even, you know, work issues like work regulations. You have to comply both with the US regulations and with local Chilean regulations when it comes to safety and, I don't know, the number of hours reporting and scheduling. So there is actually a lot of hoops to jump through when it comes to an international location. And geographically speaking, there is a lot of things to think about too.
Obviously, an enormous amount of work going into this, and
Yeah,
it's
yeah.
so amazing to see what is happening and the possibilities that are coming. Thank you so much, Chris. We're
Yeah.
almost out of time.
Yeah, sorry.
This has been just so amazingly fascinating. Absolutely love it. Just one more slide that I wanted to share. What's coming up next? So for July Space Data Hackers, we're going to have Umbra Space going back to the satellites. Their tagline is delivering global omniscience. And we will have somebody from Amazon Web Services talking about space and AI. That was a popular topic at Space Week a couple weeks back, and looking forward to bringing it to Space Data Hackers. Thank you everyone for joining. I'm gonna stop my share, stop the recording, and we'll look to see y'all next time.
Bye-bye. Thank you. Good job, Chris. That was
Thank you so much.
Thank you
Chris.
very much.
Excellent.
That was